small battery-powered test probe that you plug into the endpoints of coax networks that you are testing. So you would normally work with a minimum of 2 of them, and depending on how many endpoints there are on the network, you would attach 1 probe to each different spot, and 1 probe would be designated as the master. So they assist in identifying where the cable runs are in the home, which endpoints are on which cable runs, identifying problems with noise or ingress getting into the network. You can test the different coax paths for excessive loss across the network on the various bands that you might be concerned with. Locating points where you get strong reflections or faults on the network, where you might have poor connectors or bad splitters or barrels. And it maps out the network, does a pretty good job of mapping out the network so that you can see where splitters are, if you have amplifiers or filters in the network, and just where they are within the network. The Smartid technology was originally developed in Indianapolis, all the hardware, firmware, and the initial library. And then we've adapted it in Salem for use in in-home testing of HIPAA networks on the Smart Class Home and the Triple Play. So for somebody that's never seen a Smartid, this is what it looks like, front and back. There's not too much to point out. The identifier label is just a press-on label. It can be anything from A to Z. You just have to match it up with whatever you register the probe as when you register probes on the meter. We'll get to that a little later. There's an on-off button, the flashing status light, which is explained at the bottom, the different ways in which it can flash, and a USB connector to attach a single master probe to the test instrument, the Smart Class Home or the DSAM. On the back, you have the F connector, which attaches to the coax network, and then a battery compartment beneath it. So that is what a Smartid looks like. And this is the block diagram. It's a very simplified block diagram that just shows the essential functions that the Smartid deals with. The main elements that I'm trying to point out here, it's a smart device. It has a TI controller on it. It has a continuous wave, or a sine wave transmit source with a programmable frequency from 2 to 1675 megahertz. The RF switch is used for signaling between the probes, basically telemetry, and it runs nominally at 125 kilobits per second. That's the serial I/O that turns it on and off. And over to the right, there's a power detector that receives the input from the F connector, runs it through a comparator. That's the receive side of the signaling, and that's how these probes communicate with each other when they're not actually running a test. The RF power level detector is used not just for generating for receiving the signal and indicating an on-off condition, but it's also used for an accurate power measurement across a broad band. It has a pretty good range of capability there. And that is what's used to measure power on sweep tests that are end-to-end sweep tests, not FDR tests. The FDR tests rely on a separate level detection mechanism, and I've left out a lot of elements in the block diagram, so just understand this is a very simple block diagram. And the last thing I want to point out is the RF switch up in the right, up at the top. The Smartid has the capability of switching itself to a 75 ohm internal termination for calibration purposes and to establish a noise floor, and a reference FDR before it actually switches out to the cable. But when it's in that reference, that position that it's shown at right now, it also has a secondary effect that is used to good effect, where it basically makes the probe a high impedance termination and generates a strong reflection. Whereas when the switch is in its normal position to the top, it will act as a normal termination in receiving. I'll show later how that comes into play. That's used to identify the position of remote probes across the network. Okay, so what can Smart IDs do? This is just a brief list of the specifications. It's not complete, but these are the key elements. And I don't know if we need to go through all of them in detail. The main things are just that it has a broad range you can sweep over in increments down to 100 kilohertz. Sweeps are done at either a low power 40 millivolt dBmV level, or actually I think that should be millivolts, not dBmV. That's an error there. Oh, I'm sorry, this is on the receive side. Okay, I think on the receive side, the dynamic range is 60 dB. On the transmit side, this shouldn't be in there. I have to apologize for these goof-ups. I'm just seeing them right now. And the transmitter for the FDR works essentially the same, has the same specs. The TDR that's derived from the FDR will go out beyond 300 feet with a resolution. It's spec'd at 6 inches, but it's probably closer to a foot in actual, in practice. One other thing I want to point out is that when you're doing end-to-end sweeps, which is the RF sweep, that it takes about 2 milliseconds per frequency to move through a range of sweeps. So if you're doing like a 300-point sweep, you're talking about 0.6 of a second per sweep. And the FDRs normally involve 1,000 points or 1024 points, so they take about a second per sweep. And this thing does a lot of sweeps when you're doing the test, so that the time adds up a little bit. Okay, Smart ID functions. These are things that we've just talked about briefly, but this is going to get more into how we're using them. The RF input level measurement is how we measure noise on the cable, on the network, with all the Smart IDs in passive or receive-only mode, where they shouldn't be generating any noise. And we also use that for measuring network loss over any given network path between any two probes when a different Smart ID is transmitting the reference test signal. So we move from one probe to the next, sweeping the network, and all the other probes listen and measure the level that they receive to determine what the loss is from any given path on the network.
Question. In the noise measurement, is that a spectral result or is that a power result or wideband?
It's a broadband measure and it's power. We report it in dBmV, actually, is how we report it.
Thank you very much.
Okay. The next item is the programmable transmitter, which I'm kind of repeating the ranges of it. The FDR, we actually run a 1024-point sweep from 5 to 1028.5 megahertz. The transmitter also acts as a source for sweep tests, which we do a number of different sweep tests depending on the application being tested. And that is also used to communicate with other Smart IDs. Okay, and one last thing I'm mentioning here is there's a USB attachment for the master probe. It's a USB 2.0 connection with a CDC ACM class device, and it also features the firmware has low power sleep mode that extends the battery life on it. Okay, the USB attachment, the master Smart ID probe is the probe that is attached to the device that you're using to test the network with. I should mention up front that my work has all been with the Smart class instruments, so I've tried to provide some information on the DSAM, but if there's any inaccuracies on it, I apologize for that in advance. I've tried to make sure it's as accurate as possible, but most of the examples that I use will be from the Smart class home because that's where I really have the best knowledge. So the master probe, you only attach one of these to a test instrument. If you were to connect another master probe on the same network to a different USB port, on another device, that other probe would also think it was a master. And when a probe thinks it's a master, it will not respond to any commands from other probes. It only initiates commands. So you only want one master probe on a network. So all test operations are directed by commands to the master from the controlling instrument. The master probe will pass on commands that are really aimed at the slave probe to execute whatever is required and to retrieve test results back and pass them on to the meter. And slave probes never transmit except in response to commands from the master.
A question on that one, Tom.
Yes.
Does the user have the capability to select which commands we want to send to the slave?
That's all done automatically. The testing is done at a much higher level. They select an overall test operation which runs through a whole series of commands, setups, and operations to be done. So it's all automated. The user just requests an overall test be done.
Okay.
And the smart IDs are all the same. By plugging in the USB, you make one a master, right?
That's correct. Any probe can be a master. Okay, the noise level measurements. I'm probably myself a fair amount here. The noise level is actually an RF log detector, so it's going to generate an output that's linearly proportional to the log of the level. So it's a power. It's like a logarithmic scale as in decibels. Okay, the master probe, when you start a test, the first thing that happens is the master probe is initially checked for the presence of excessive noise, which could be other devices on the network, before running sweep tests or attempting to communicate with other probes. And that's because when you connect to a network, you don't know if you're going to be, especially if you're out in neighborhoods in cable TV networks where they'll share connections, you might actually disrupt neighboring services. If you're connected to DSL, you might disrupt the DSL connection somehow. And also, you just don't want a lot of noise if you're going to try to get accurate results on your FDR or sweep tests. So if there's excessive noise, then everything stops right then, and it just reports that there's too much noise on the network. That is different than the actual noise level measured at each probe during a test and subjected to a pass-fail condition. That's a much more refined measurement and will fail at a lower noise level. Will be marked as a failed test. So the broadband noise level measured at each probe is used to basically identify noise from damaged shielding, bad compression fittings, or active noise sources that are at a lower level. Okay, sweep measurements. These are like end-to-end sweep measurements where you're trying to measure loss through the network as opposed to a return loss or a reflected signal. So I kind of explain the steps that are involved in it here. A single probe designated as the master, or as the transmitter, not the master. This can be any probe. Generates a series of tones over a specified frequency range, starting with the lowest and progressing at regular intervals until the full range is tested. These sweeps are the ones that run at 2 millisecond intervals. Any probe can be designated as a sweep transmitter. All others act as receivers. Each tone is sent by the sender for 2 milliseconds, and he automatically steps from tone to tone. The receivers have to keep step. They need to have 1 millisecond of accurate measurement time, which is half the 2 millisecond overall interval. The extra time is to allow for slips in timing, drift between the master and the slaves. But the master probe initiates the whole thing with a single command that identifies the transmitting probe, and everybody else should start listening and start their reference time at the same point in time. FDR measurements, this is where you're actually looking for reflected power back from the sender, which is why he only needs 1 millisecond per interval, because there's nobody else that's out there measuring what's being done there. He's the only one measuring the reflected power back to himself. So the master probe broadcasts a single FDR command containing the ID of the probe to run the test, which is the transmitter, and optionally the ID of a second smart ID to be placed in a high impedance or mismatched state. Any other smart IDs out there automatically attach themselves in a normal termination so that they don't generate an extra reflection. So if you want to get an FDR with a high impedance on one designated remote ID, you include his ID. If you don't, if you want everybody listening normally, then you just put in the same ID as the transmitter for the second ID.
When would you use that?
Basically, what you're doing is you're going to generate a reference. This is done from the master probe. We'll do a single reference FDR with everybody terminated so that he sees a normal reflection pattern on the network. And then one by one, he will turn each one of the slave probes to a high impedance state and run a sweep with that probe in a high impedance state. And it's the difference between each of those and the reference sweep should be caused by that difference in the remote reflection. So the spike in the TDR at that point should make that slave probe stand out. Here's where I am.
So that will give you the distance from the master, from the transmitter to that high impedance probe.
That's correct. That is its purpose.
Okay.
Okay. Whoops. What did I do? Okay. All right. So the return signal strength is measured at the sending probe for each tone. All other smart IDs remain idle, whether they're in a high impedance state or just in a normal state. And the FDR results are retrieved from the transmitting probe after the test is complete. Okay, this is the third section, how are smart IDs used? Now I'm not going to try to talk about how we're actually running tests with these things from an overall perspective. So the DSAM uses smart IDs for testing basically your regular cable networks with or without MoCA in the home. And I show the three different bands that MoCA operates over. I'm not quite sure if the DSAM supports testing on all these bands or not. If there's somebody out there that knows the answer, maybe you can chime in. And I say that MoCA relies on upstream signals reflected back into the network at the MoCA filter for set-top box communication. But I have also seen special splitters designed for MoCA, so perhaps they are allowing what I call cross-stream communications between the outputs of a splitter right in the splitter itself. So I'm trying to give the information as accurately as I can here. Unfortunately, I'm not an expert by any means on MoCA. So, but the DSAM, when he will run a set of sweep tests in the MoCA band, when you designate the test to include MoCA, that he analyzes to produce a quality index for MoCA, which is designated as the MoCA quality index, ranges from 0 to 10, with 10 being the best performance and 0 being worthless. So, okay, Smart Class Home Triple Play Smart ID tests. The Smart Class Home and the Triple Play use Smart IDs for in-home networks that are designed for HIPNA, which is a radically different critter than MoCA. It operates down at the low end of the spectrum, and I show the different modes that are defined for it. The key one that is being used now by AT&T is Mode B, which runs from 12 to 28. Stuff down below 12 megahertz is probably not going to get used much because DSL runs up to 8.5, I think. So Mode A probably won't be used by anybody, but we cover in our testing out to 52 megahertz just in case some of these other modes start to get picked up. And HIPNA, the key difference is that HIPNA relies on non-directional splitters to distribute HIPNA signals across all network paths. Regular cable networks use directional splitters where the loss upstream and downstream, in other words, between your outside connection feeding into your home. For example, you might run through a 2-to-1 splitter. The outputs of that splitter would only drop typically 3.5 dB going to the input or input to the output. But if you try to communicate between the outputs, they are designed for high isolation, and your loss will typically be in excess of 30 dB. Whereas a HIPNA splitter, you want it to look more like a star point connection, where the signal will distribute evenly along all paths. So that increases the loss of the HIPNA splitter, upstream and downstream, but makes it the same also, and significantly drops the loss between the outputs of the HIPNA splitter. That also creates problems for mapping, which we'll get to a little bit later here. Okay, the DSAM tests, these are the actual tests that are currently defined for the DSAM. There's a drop check and a voice video data check that don't include MoCA. They involve locate IDs tests, which I haven't described yet, but we'll get to that in a minute. Noise level check, an upstream loss sweep from 5 to 40 megahertz, a downstream loss sweep from 55 to 1,000 megahertz, and then the network mapping, which is a series of FDR tests and a loss test over a broad spectrum to look for filters and amplifiers. The tests are essentially identical, except the drop test is designed for a single cable run with 2 endpoints and has much tighter pass-fail limits than the other. The voice video data plus MoCA is the same as what I just described, but also includes a cross-stream sweep test between all of the MoCA endpoints to test for loss between the endpoints, for MoCA traffic. And they have a bunch of different channels that you can be operating on. There's a default channel of D1 that tests from 1127 to 1172. I know MoCA runs over potentially anywhere from as low as somewhere around 500 megahertz to up around 1650 megahertz, thereabouts, depending on which version of MoCA you're using and which channels you're using. Okay, Smartid testing with the home and the TPS. These are the tests that are defined for the Smart Class home. I don't know if they're going to be exactly the same on the triple play, but Locate IDs test, which was run as part of the test on the DSAM, is also provided as a separate test on the Smart Class home. That's basically a test that just runs out and finds which probes are on the network, or at least which probes can it see on the network. A fast scan is kind of a variant of that lets you, it keeps a continuous scan going and lets you quickly identify when you pop cables on and off the network, which probes are being added or dropped from the network as you do that, so that you can quickly identify cable runs. The home run test is similar to the drop check. It's a 2 probe test. And you're just looking for a clean cable between the two ends. But it does include the full range of checks. You check for IDs, you check for noise, you run a sweep test, FDR tests, and mapping tests on the whole thing. The whole home check is, with the diplexer and without the diplexer, are basically the same test. They run the full battery of tests, but they involve different checks on the outcome for passing and failing. Okay. When you go to use these things, the first thing you have to do is tell the device that you're testing with which probes you have and what letters you want to represent them with. So each probe has a serial number built into it, which is used as a MAC address, in communicating with the probe. And when you attach the probe to device with the USB cable. It can quickly read the serial number, and you can use that to quickly register a set of probes. So each Smart ID to be used with a test meter must be registered on the meter. Each Smart ID is assigned a letter from A to Z at registration time designated by the user, hopefully matching the letter they've got pasted on the thing. And each test meter can support up to 16 Smart IDs.
So is the registering done once per test set, really, or at the beginning of every test?
No, you just register your probes. So when you get a set of probes, the technician would register those on his meter, and then the registration stays there.
Right.
And until he has to replace a probe or add some more probes or whatever, then he doesn't have to disturb the registration.
And he does that by connecting the main, by connecting the probes individually through the USB.
Yeah, I mean, he can
Right.
manually enter the serial number also, but the smart way is just to attach it and let it read the serial number and put it up on it, and then he can, okay.
Thank you very much.
Okay. Okay, when you go to test, this is the locate IDs test, what I call the locate IDs test. So when you first bring up your test meter, it will ask you to attach a probe, and if you haven't already done that, and turn it on. And then it should identify the master probe through the USB connection when you first bring it up. And then when you start the locate IDs test, after the master probe is identified, the master will then pull all the other probes that you have registered and find out which ones are out there and what frequency is best to talk to the probe. We'll check for 3 different frequencies to talk to the probe. And basically just put up a list of everything that it found. It will also, probes that are not registered will not be pulled. So if you attach an unregistered probe to your network and turn it on, it might be there and capable of responding, but since it's never pulled, it will never be found. So each probe which is found reports the probe's noise level measurement, firmware revision, and the battery condition back to the master. And that particular screenshot shown in the upper right doesn't show anything there, but it would report which probes had a low battery condition or old firmware as part of that report if any probes were found in that state. So it does take a few seconds for it to go through this test. If you have more than 10 probes, it'll probably take maybe a dozen seconds or maybe a little more to actually scan all of them. It has to allow some extra time for response to first-time polls, because these probes will go after 30 seconds of idle time. They'll go into a standby state where they only wake up once every 5 seconds for a tenth of a second or so to check for any traffic and to see if anybody's trying to talk to them. Okay, the fast scan test, I think I've already described it in some detail, but this is only on the Smart Fast Home and the TPS. The DSAM I don't think is using this feature, but it provides a quick visual indication when probes are disconnected. It should show them drop out of the list in less than 3 seconds, or when a probe's connected. When it's connected and you disconnect it, it will take up to 3 seconds, and when you connect a disconnected probe, it should happen quicker than that. It actually happens within a second and a half or so. So it's used to identify cable runs in a home, but because you're constantly pounding the network with poles and the remote probes are constantly generating responses, that tends to drain the battery at a faster than normal clip. So we limit the duration of the scan to 60 seconds by default, which you can up to 90 seconds. And a tech, if he needs to extend the scan, he can just push a button on one of the soft key buttons. It'll just restart the scan anytime, and he can stop it anytime he wants. Okay, DSAM sweep tests. The DSAM sweep tests are run from 5 to 1500 megahertz in 5 megahertz steps. Results are gathered from the master probe from each slave probe sweep, and from all of the slave probes for the master probe suite. Sorry, I said that wrong. The results are gathered from the master probe for each slave probe suite, and from all the slave probes for the master probe suite. The upstream and downstream sweep data is checked against predefined configurable limits, and when MoCA is also tested, there's an additional sweep test run over the MoCA band. So when after the data is analyzed and presented, it's presented in what we call pyramid form. It's actually like a half pyramid. The leftmost column of that pyramid is the upstream-downstream results, which do not include MoCA, because MoCA is used to communicate across stream. But everything to the right of that first column is MoCA results, which is why you see a number there instead of an X or a check mark. And that is the measured MoCA quality index for that path. HypnoSweep tests are similar, except the HypnoSweep tests are really run on the Hypno band from 2 to 52 megahertz in 100K steps. These sweep results are gathered up and checked against the predefined limits for min-max loss, loss variation, and other parameters which can optionally be defined for determining whether the test passes or fails across that band. The pyramid on the Smart Class Home, since we don't have a MoCA quality index, everything is shown with a check mark or an X. It's either a pass or a fail. The leftmost column is still your upstream, downstream, and everything to the right of that is communications across stream. But when I say cross stream, I'm talking about between what you would consider the outputs of a network. I'll try to explain that terminology a little better when I get to a network example. The SmartIDs also run a 5 to 1500 megahertz sweep test for mapping purposes in the same way that the DSAM does, but it's only used for mapping. Okay. Just to explain cross-stream, all these points numbered 1, 2, 3, down to 6, these would be what I would call, normally in a test you would attach slave probes to here, and you would attach your master probe down at the base of the network that feeds into it. Cross-stream would be communications between any of these endpoints on the right. Whereas upstream, downstream, upstream would be like from 1 to M, downstream would be from M to 1, just to explain the terminology. That next slide. Okay, so this is a HypnoSweep test example, just to show what the results look like. This is tested with hypnosplitters, excluding the tap, because there is no such thing as a hypnotap that I'm aware of. So there's a 75 ohm terminator placed at the connection point labeled 6, so that you don't generate any reflections on that. And this is the output that you get. It's a clean network, so everything comes up green. The only thing you see a little bit of variation in the loss. The actual averages, if you look carefully, you can actually see that the A to D path averages somewhere around minus 16 dB, because it has to pass through a couple splitters. Whereas the A to B and the A to C look more like 12 dB. A, B, C. Okay, I'm sorry. There would be 3 splitters. What this is the higher loss is between any of these two coming across to any of these two, because it has to go through this path as opposed to just across one splitter. But other than that, everything's pretty straightforward here.
Is there a particular reason why those graphs are filled in as opposed to having lines connecting them?
Just that was just the method chosen to represent them. Nothing more than that.
Thanks.
Who sets the pass-fail criteria? I'm sure GDSU does the first cut, but do they have the capability to change it, or do they have to ask us to change it for them?
They can't change it in the field on the meter. They can give us, if they want a new set of limits, they could request that we create another file for them that there is a means to upgrade using the conventional upgrade method that upgrades only the Smartid configuration.
So it's a separate configuration file on the unit, not hard-coded.
That's correct.
But they can't do it themselves.
No, not the way we've done it right now. Okay, so just showing a couple more screens that are presented. This is the detail view. And did I show the map in the previous one? I guess I did. On any given path, you can look at the detail to see, if you select the endpoints, it also shows you the noise measurement at that endpoint. So you see a minus 19 dBmV measured at probe A and a minus 24 dBmV measured at probe D. The intervening points, when we start talking about the mapping, then we'll get into those. So network mapping is all about the FDR tests, which I'm just basically summarizing things that I've already said here, details of process of running the FDR sweeps, measuring the data, collecting the data, running it through an FFT transformation to generate basically a time domain reflection pattern instead of frequency domain, with an effective resolution of about 10 inches for the TDR. Here's where you get into all the different sweeps that we run. A single FDR test is run from the master probe with all of the probes set for normal line termination. That's basically a reference, that's like the normal downstream trace. There's also, I should mention one other thing. We do take a reference sweep where you have the 75 ohm terminator connected in internally. That's like your ground floor sweep. So anything that you get when you connect it to the actual cable network, you have to adjust it for the ground floor sweep to account for any internal variations on the, in the hardware itself. Then, so we run the single sweep from the master with all of the probes in normal termination. Then you run another FDR test from the master for each slave, with that slave placed in a high impedance mismatch state. Then two tests are run for each slave probe, one with the master probe normally terminated and one with the master probe in a high impedance mismatch state. And the same FDR tests are used for all applications, the DSAM, Smartid, they all work the same in that way. In addition to the FDR tests, we take mapping sweeps, which is the 5 to 1500 megahertz, which I've already mentioned. The key point here is that those are used to find, when you examine the response across any path, you can find out where you can have high-pass filters, low-pass filters. You can look for gain for amplifiers in the forward direction or in the backward direction if it's a two-way amplifier across the bands that they are supported on. So all those network elements are identified in that way using the network mapping or the network sweep tests over the 5 to 1500 megahertz range. On the DSAM, this set of sweep tests is used for both loss measurement and for mapping. On the Smart Class Home, it's only used for mapping. Okay, HIPNA mapping example. You attach in a normal way with the master on the left, your slave probes connected up on 1 to 5, and the 75 ohm terminator at 6. So this is the same network I showed the sweeps on earlier. And you get the results, and down in the lower left you see the results of the mapping analysis, which if you go back, you don't see the tap there. I'll get to that in a second, but there's a two-way splitter feeding into a two-way and a three-way, which is accurately represented. And if you look at the detail view in the upper right, which is, you notice on the map that A and D are the two selected endpoints that have squares around them. So the detail will show from A to D. The first reflection is reported at 10.6 feet, which is the length of the cable that attaches from the Smartid to point M on the reference network, from the master probe to point M. Then you have 20 feet to the tap. And if you look at the next one beneath it, he reports the second reflection at 30 feet, which is 20 feet beyond the one above it. That's where the tap is coming into play. And then the third reflection point, which I didn't show the distance, but I know this map did come out accurately, is the first splitter. And if you go down and look at the others, all the endpoints check out correctly on here. So in this particular example, it maps everything out very accurately.
Why is there no exclamation point?
The exclamation point was just that's what we refer to as a fault. It's basically, the difference between that and a splitter is that a fault is a reflection that is, there's no splitting of the network, of the cable path at that point. It's just a point where a reflection beyond a certain minimum has been detected. So it's reporting that, hey, we're seeing a reflection here. It might be a crimped cable. It could be like a tap stuck in the line. It could be a barrel that's, less than perfect, or most barrels, a lot of barrels will show up, some won't. The better the barrel connection, the more inclined it is to not show up. So anything showing up is a candidate for potential replacement. Okay, so how's the sweep ID data analyzed? The DSAM performs the MoCA sweep, a detailed analysis of the MoCA sweep to generate the MQI, which takes into account, this is straight out of something I got from Indianapolis. It takes into account the entire 50 megahertz MoCA channel. MoCA is made up of subcarriers that will adjust their modulation if that specific frequency is unsuitable. So what they're doing is analyzing and looking at these subcarrier frequencies to generate a score indicating whether they think that subcarrier will be useful or not. And the score basically is proportionate to how much throughput you can expect to get on that path in your network over the MoCA connection. HIPNA is, because it's so different, it's only got one carrier, it doesn't have the multiple subcarriers. So the analysis is really just looking for excessive loss across the spectrum or excessive loss swings within the spectrum. There's additional parameters we can look at, but those are the key ones we're looking at right now. The pass-fail limits can be fine-tuned if you need to by dividing the sweep results into different bands and checking them in different bands. We also check in some instances for a certain minimum loss, where in cases such as a diplexer where you actually want to have a high isolation from a certain part of your spectrum. Okay, the process of generating the map, this is where things get a little tricky. The downstream TDR with the normal termination is compared against the downstream high impedance termination for each master-slave probe to determine the location of the mismatched probe. That's done for each slave probe to determine its distance from the master. The upstream TDR is then processed for each slave probe to look for significant reflection points along that path. Reflections from the upstream TDRs are sorted into a common list of reflections that is then processed to identify common reflection points and places where splitters would occur. I'm going to explain this quickly and move to the examples because I think the examples do a much better job of showing what's going on. Splitters are identified by the points at which reflections or path characteristics don't match up. The amplifiers or filter elements are inserted at the furthest common upstream point at which that element is detected. So I'll just leave that there as an overall statement and move on to show some of the details. Oh, I need to mention this too. That mapping enhancements are, because HIPNA splitters are non-directional, so upstream TDRs have reflections from other slave probes in pretty much the same way as a downstream TDR does on a regular network from all the upstream probes. So the extra reflections, just to make a long story short, because I'm running a little short on time here, the extra reflections create a lot of havoc if you don't do something to filter them out. So this series of bullet points is really a word explanation of the steps that are taken to eliminate those extra reflections from the mapping, from the TDRs, so that you can get an accurate map without a lot of extra reflections reported. I want to move to this example here because I think it shows it much better than words. Here you've got a simple 2-to-1 splitter. So your TDR looking from A is going to show a single reflection 30 feet down at the first splitter. 10 feet after that, he's going to show a reflection at B, and 20 feet after the splitter, he's going to show a reflection at C. So this is what the TDR should look like from A, looking downstream. Looking back from B, when he runs his TDR, he's going to see 10 feet going back to the splitter. 20 feet after that, he's going to get the reflection from the C probe because this path is in play just as this path is. And then 30 feet after the splitter, he's going to get the reflection from A. And the TDR from C, looking back, is going to be the same, 20 feet back to the splitter, an additional 10 feet to B, and an additional 30 feet from the splitter to A. So what I'm doing, since I know the end-to-end distance of these probes, I basically reverse this so that you are now looking at a mirrored view of the TDR. So this reflection here is the false reflection that we don't want to see from C. My cursor keeps dropping out on me. And these are the true reflections. Well, you can see from the way it's lined up. Basically, what I'm doing is correlating the downstream sweep with the mirrored upstream sweep. And in the places where I have common reflections, then I know they're legitimate. But these reflections from other points downstream, which I don't want to see when I'm looking back from here, will be dropped out. And you see the same thing. Same thing here. This is the mirrored TDR looking, from C, and the B is going to be 10 feet this direction, looking downstream, and 10 feet this direction when you're looking upstream. And so when you correlate these two, get rid of the extra reflection. So that's the key thing. The final piece of the puzzle is how I'm putting it all together. Because as you go further upstream or downstream from either end, your reflections are getting weaker because they're going through successive levels of attenuation through these splitters. And so at the extremes, it doesn't work very well to try to correlate the extremes. So the key is that what I'm generating overall is a composite TDR that uses the best results on the front end are from the downstream. Best results from this end is the upstream TDR, and what I refer to as the interior of the network is where I'm applying this correlation process, which is just a mathematical product between the two sweeps that relies on an accurate distance measurement.
Question. Do you not use the sweep results for the known forward power drops in figuring out where these things are?
That's one of the items you're anticipating. That's on the list of possible enhancements that's being looked at. Because with HIPNA splitters, you can actually make some intelligent decisions that way. The problem is that with directional splitters, you can't rely on that loss across stream. And so it's not clear that it will work in that approach. But that's one of the things that's being explored.
Thanks.
Okay, this is about 5 minutes. Oh, I have 5 minutes. Okay. I'm going to have to move fast. All right, this is some actual examples. This is the raw TDR from the master probe. And I can't remember, is this hypno splitters? Yeah, this is hypno splitters. Okay, this is the master probe with the probe D in high impedance state. This is just on probe D here. And if you look at this one right here, you can see that it sticks out when you switch it to the high impedance state. This is the actual graph of the composite, of the differential TDR, and it picks out with good accuracy the point at which the distance to that probe. Then the composite TDR is generated. This is D to A looking upstream. And down here in particular, you've got a lot of extra reflections that would show up in the original approach as a lot of rat-a-tat-tat reflections down at the end by the master probe. And you've got extra reflections up here. But when you do the composite, then you get clean stuff here in the middle, and this picks it out pretty accurately. And then you take the mirrored image. This shows actually 2 probes. And this is the reflection pattern that actually picks out from the composite TDR. And 26, this is the bin number, the index basically. Each one of these represents about, I don't know, 5 inches or so, maybe 10. But 26 is your reflection at the 10-foot mark. 75 is your reflection at the tap, about 30 feet in. 124 is the first splitter. The reason why it's detected as a splitter is because you have different lengths on the next run. So these have to be going to 2 different places. They can't be going to the same place. These are combined, detected as being common, but here splitting out again. And these things with the square braces around them are the endpoint distances. So that's how it actually pulls out, analyzes the TDR reflection pattern and pulls out the mapping of the network. The filters and amplifiers would be inserted at appropriate points based on the loss measurements. You know, across each path you would see the filters on this path and not on that path. And that's how you understand where to put them in. So, and that's the network map in detail. And here I highlighted all the individual things. I'm running short on time, so I'm going to have to wrap this up. With directional splitters, CATV splitters. Okay, this shows the results on this is talking about the sweep results here. We have directional CATV splitters. So looking upstream, downstream, everything looks good. You look cross stream, B to C, C to D, D to E, you can see you've got all kinds of grief because you're getting, basically what's happening is when these guys try to talk to each other, you're getting reflections back from these points that are delayed, and it just combines and you get a lot of comb filter effects and things of that kind, and you get a mess that looks like this that doesn't work worth a darn. Mapping with the directional splitters works pretty good. I show the same basic sequence, pulling out the distance. The distance I've got marked with a cursor here. Then here, this is the composite TDR, and this reflection here is diminished a little bit by the correlation, but it's not diminished excessively. So in this case, because it is directional splitters, this pattern is actually clean, and you don't have to take this step, but it doesn't hurt you to do this. In all the testing I've done, the directional splitters, we seem to pick it up pretty good. We don't seem to hurt the mapping with the correlation process. So this shows how the reflections are finally analyzed and grouped into the map. All this red is because these paths fail the loss test across those paths. That's why they're marked in red. Okay, Smartid mapping limitations. The Smartid FDR sweeps are limited in resolution. Cable lengths of less than a foot between splitters, barrels, and Smartids generally won't be picked up right. Splitters may not be located correctly when you have additional downstream reflections detected at the same position relative to the master. And it gets kind of complicated explaining this, but there is a configurable thing called a patch cable length that is basically a distance within which it won't try to combine, won't try to merge a common reflection point into a splitter. An example of this, just to make it a little clearer, is if you had a splitter stuck behind a wall somewhere and you had two 20-foot runs from each output of the splitter to two different wall outlets with barrels in them. What that would look in your reflection pattern would be like a 20-foot reflection at one point and a 20-foot reflection 20 feet, or another 20-foot beyond that you'd see another reflection. So you would expect the splitter to be at the last point, first point of where you get it, where you might see a difference in, or where the probes are attached. But in fact, those are just barrels. And it's because the run to the previous splitter is identical in length that they're susceptible to being combined into a single splitter. So that's what the patch cable length is a little bit of a kludge to cover that. Okay, large HIPMAN networks with a lot of endpoints are prone to mapping errors because there's too many reflections, and even with the correlation, you're going to run into too many other places where it's going to falsely correlate because there's just too many reflections. And the last point that I make here is that you have to have an accurate distance between the master and slave for this correlation to work, because it depends on mirrored data correlating with the downstream data. So if you have a situation with a network where you just aren't getting a good reading on the high impedance termination at a slave probe, it can generate misleading mappings. So I just want to quickly show an example here. This is an example of resolution. You notice that the connects here are all very short, 12 inches, 6 inches, and 18 inches. What this results to in the map, it does succeed in resolving the 18 inches, but it does not resolve the two smaller ones. And I show some examples there, but because I'm actually over time, I'm going to move on. The misplaced splitter example here, there's a couple of these probes that were connected out with, I don't know, 10-foot cable or something like that. They had a long cable length on these two, longer than the rest of them. So this cable length extended out beyond the patch cable length, and so it allowed it to pick up as an extra splitter here. But if you increase that patch cable length to 10 feet or more, then those 2 points out there, right here, show up as part of this splitter as a 3-to-1, which is the correct mapping. Noise detection is another limitation in the sense that it relies on an absolute noise measurement. If you don't have enough ambient noise at the time of taking the measurement, you may not detect that you have poor shielding. And also, on the HIPMA pass-fail limits, in actual testing, what we observed is that when you get close to the edge, you can have Smartid networks that pass the Smartid test but still have HIPMA packet level test failures, and vice versa. We don't have right now a marginal, like a yellow region, a warning region where we indicate that you're close to the edge. So that's why we get these kinds of conditions. I talked briefly about some possible enhancements, cross-stream FDR sweeps, which could be used to resolve ambiguities and get rid of that patch cable length thing so that you know exactly how far between you are between different slave probes. The problem is that those probably won't work properly with directional splitters. You would have to know that you had HIPMA splitters on there for that to work correctly. And here's where I also make mention of the analysis of the cross-stream loss to help resolving mapping ambiguities. There is also possible test time enhancements. I don't need to go into that. I want to mention that there is additional information out there. If anybody wants to try to contact either of these individuals in Indianapolis, there's some very in-depth stuff that goes into more technical detail than I have here on the smart IDs and how the mapping is done. So I'm 5 minutes over. If anybody has any questions, I'll be glad to answer them.
FDR, do you know if it's just magnitude or is also part of the?
It's just magnitude. You get 2040 points going in, 24. Yeah, because I guess you drop the complex conjugates.
Right.
It's just a real straight level. Okay. What's that looking for?
Right there.
Okay, I still see a couple of people on from outside. Is there anybody else with questions? Okay, I will try to get an email out to everybody directing them to where this information is posted on SharePoint. And thank you all, and I think we're done.
Thanks.
Thanks, Tom.
I was going to hang up.